So today we're going to discuss a new topic of noise and intermodulation distortion. Probably this topic of noise is not new to you. I'm just going to review some of major points associated with noise that are relevant for design of RF. And then another important point is intermodulation distortion, okay? Because the devices that we have in practice, they all exhibit nonlinearities, they are nonlinear, which means that if you apply a sine wave at the input, the output is not just the sine wave itself at that frequency, but contains other frequencies. Okay. For example, amplifiers are nonlinear. Obviously, we can operate them in certain regions where they are approximately linear, but the impact of the intermodulation distortion on, for example, communication system is very important. That's why we're going to see this today. And so, with respect to noise, we're going to discuss the types of noises, and obviously, white noise is one of the important noise that that is relevant in most electronic circuits. We're going to define the noise equivalent temperature and the noise figure. Okay. With respect to nonlinearities and nonlinear distortion, we're going to see a simple model that we're going to use to define the nonlinearity of the device. We're going to define gain compression and intermodulation distortion, because these are the two, let's say, parameters of a device that specify the nonlinearity of the device. And then, and based on this, we also can define a dynamic range of operation of a device. So, with respect to noise, obviously we have thermal noise, which is associated with the random motion of charge carriers generated in passive circuits. For example, in a resistor. We have shot noise, which is the random motion associated in active devices, solid-state devices like transistors. And we have plasma noise and quantum noise. We are not going to discuss this. Just for information, plasma noise is associated with the random motion of charge carriers in an ionized gas. For example, this is a type of noise that is relevant, for example, in satellite communications due to ionized gas in the atmosphere. And also quantum noise is due to the discrete nature of photons and electrons. For example, which occurs when you have photo detection, for example, of optical signals and on a photodiode. We have conversion of electrons to photons to electrons, and this conversion is discrete because we have discrete particles that are being converted, and they and this quantum noise follows a different probability distribution. And the most common one associated with thermal noise, as we're going to see, is Gaussian probability distribution, but quantum noise follows a Poisson distribution. Okay. If we have a certain, for example, a resistor as shown here in this figure here, at the terminals of the resistor we have a certain voltage. Due to noise on the resistor, thermal noise, we have a fluctuation of the voltage at the output at the terminals of the resistor. A possible case is shown here with the variation of the voltage at the terminals of the resistor. The mean voltage will be zero, which means on average the voltage is zero, but the root mean squared, which is calculated by taking the square of the voltage at the output and calculating the average and then taking the square root of this, so it's the root mean square, over a certain frequency is non-zero. And it's possible to show that the voltage, the voltage RMS, root mean square voltage, is given by this equation here, which depends on the temperature of the resistor, depends on its value, and also on the bandwidth over which you are measuring the noise. And there's a constant here, which is the Boltzmann constant. One important parameter is the available noise power, which is the maximum transfer of power when the load impedance is the conjugate of the source. So we have already seen that the maximum power that you can extract from the source is using a matched load or a conjugate load of the source for maximum transfer of power in case the source has a complex impedance. So what we have here is a resistor with a certain noise. This is modeled here in this picture as a resistor, as an ideal resistor with no noise, and the noise is represented here as a separate source voltage. Okay. If we want to measure the available noise power over a certain frequency, here we have, this has to be measured over a certain frequency band, which is represented here by this ideal bandpass filter. And for maximum transfer of power, this resistance has to be the conjugate match of the source, so it has to be the same in this case, assuming this is a real resistance. And in this case, the available power is given here. So V squared over 2 is the mean square power divided by R, gives us the total power, which since we already know that V sub n, the voltage RMS, is given by the equation that we've seen here. And so by substituting this result here, we get that the available power is just K times T times the bandwidth. And so the power spectral density associated with this noise power of the resistor is the available power, since power spectral density means power over the bandwidth. Okay. Here the bandwidth we are assuming is so if we have for example a bandpass filter over a certain band here, this filter has equivalent bandwidth at the negative frequencies. And so the total amount of power that passes the filter has to be accounted twice the bandwidth. That's why we divide it by 2 times B in this equation here. And so the total result is that the power spectral density of this source is constant. It has a constant power spectral density, and so it does not depend on bandwidth. And since it does not depend on bandwidth, if we represent the power spectral density over frequency, if you represent this like this, what we get is a constant power over all frequencies, which means that this source contains all frequencies, okay? And that's why it is called white noise, because this is a comparison with what happens in the visible spectrum, right? Because the white light contains all the colors within the visible spectrum from violet to red, okay? And when you mix all these colors, you get white. And so since this noise is flat over low frequency, it contains all the frequencies, that's why it's called white noise. Okay. And according to the central limit theorem, this tells us that white noise has a probability density function which is Gaussian. Do you know why? You know what the central limit theory says? I don't remember. It says that if we have a random variable, okay, which follows a certain distribution, okay, if you have a combination of different random variables, the combination of, as you combine more variables or more random variables, the total probability density function tends to converge to the Gaussian distribution. Okay? And since the thermal noise is a result of vibration of the atoms, and since the combination is a result of the vibration of a very large quantity of atoms, right? And the current flowing in the resistor is a result of this, depends on the vibration of the atoms. At a certain temperature, it tends to follow this Gaussian distribution, which is given by this equation here. Okay. And since the variance of two independent random variables is the sum of the individual variances, which is equivalent to the power delivered to 1 ohm load. Okay. The noise powers of two independent noise sources add that load, which means that if we have two noise sources, for example, two resistors, the total noise is obtained by adding the powers of these two sources. The powers add, not the amplitude, but the power. Okay, that's what it says. To define the noise, there are two important parameters that are equivalent. These two parameters are the noise temperature and noise figure. To define these parameters, let's consider a white noise source, as we've seen now, connected to a certain load. So we have here a white noise source connected to the load, a resistor here. And this white noise source is replaced by a resistance, which is shown here from here to here. Okay, so we go from this diagram to this one on the right, where we replace the white noise source by equivalent resistor, which generates the same amount of noise. Okay. And the resistance is chosen so that it is matched to the load, so it has the same, has to be the same value as the load, as shown here. But this resistance is at a certain temperature, which is the temperature that generates the same amount of noise as the initial arbitrary white noise source. And that's the way we define the equivalent noise temperature. So here we have a noise source that generates a noise and sub naught here. And we know that the noise generated by this resistance here is, we've seen that is KTB. But the temperature here is this equivalent temperature of the resistance. Is from here we solve this equation with respect to TE and obtain this result here. Okay. And so for measuring the equivalent noise temperature, we must measure this over a certain bandwidth, which is generally the bandwidth of the system being measured. Okay. We can define an equivalent noise temperature of an amplifier. And for that, let's consider we have a noisy amplifier, okay? And if this amplifier is connected to a source or a resistance here with a zero temperature, so in this case, if the absolute temperature is zero, then the noise generated by the resistance is zero in this case, and the amount of noise in this case that appears at the output is the noise only generated by the amplifier, because the source has no noise. Okay. Now what we do is that we equivalent model to define the equivalent noise temperature is to assume a noiseless amplifier here, whereas the noise is assumed to be generated by the same resistor at the input. Okay. And I think it's more or less obvious that in this case, the noise at the output is given by the gain times the constant times T, equivalent noise temperature of the amplifier times B, and so the equivalent noise temperature has to be the noise and sub naught divided by GKB, where G is the gain of the amplifier, which means that we only, to define the equivalent noise temperature, we have to divide by the gain of the amplifier. Okay, so if we compare this equation here with the previous one, the difference is that we have to divide by the gain of the amplifier to define the equivalent noise temperature of the amplifier. The noise figure is defined as the ratio of the signal-to-noise ratio at the input over the signal-to-noise ratio at the output. And since the noise at the output is the noise at the input plus the noise added by the system multiplied by the gain of, in the case, the amplifier. So in this case, we have the denominator is always less than the numerator. Signal-to-noise ratio at the output is always less than the signal-to-noise ratio at the input, and so the noise figure is always higher than 1 as defined here. Okay. The noise figure, as we see here on this equation, depends on the value chosen for the noise at the input, and so by convention it is assumed that the noise at the output is obtained at a specific temperature with T sub naught, which is 290 Kelvin by definition. Okay. Defining the noise figure or the equivalent noise temperature of the amplifier, it is equivalent, and so we can go from one to the other, and the relation is given by this equation here, which is relatively easy to obtain. And so if we know the noise figure, we can obtain the equivalent noise temperature or the other way around. Okay. Another important aspect is when we have a cascade of components. So we have, for example, an amplifier, and usually this comes about, for example, when we have an antenna, and then we have an amplifier, followed by a second amplifier. And this amplifier has a certain gain. Okay, this one has a certain noise figure, and this one a different noise figure. Okay, And the important point is that the noise figure of these amplifiers will establish the signal-to-noise ratio at the output. Okay? So the higher the noise is introduced by the amplifiers, the lower the signal-to-noise ratio at the output, right? Because the signal will be, assuming the gain is constant, the signal is constant, and so if we have higher noise, we have lower signal-to-noise ratio. And you might ask, but why do we need two stages of amplifications? Why don't we just put a gain with an amplifier with a higher gain, right? So what's the purpose of dividing by the gain over several stages? And the reason is sometimes you need a higher gain at the receiver. For example, even in wireless communications, or for example in Wi-Fi, the signal that the receiver is receiving can be very, very low, and so you need to amplify quite high the signal to be able to detect it. And the problem is it's difficult to design amplifiers with a very high gain. And so what you usually do is that you separate the gain over several stages, where it's easier to design those stages, because if the gain is very high, there's a quite high risk that amplifier starts to oscillate, okay, because of possible feedback paths. If the gain is very high, even a small signal gets amplified.
The bandwidth is slower.
Sorry?
And
the bandwidth will be slower. It's more difficult to design as well due to the reduced bandwidth. That's why you usually separate those into different stages. Which one of these amplifiers is the important limiting noise factor in the system? Do they contribute equally to the output signal-to-noise ratio, or does one of them contribute higher than the other? And the question is that's the question we want to answer in this case. The noise at the output of the first stage is the noise at the input, which is this factor here, assuming that we have a noise temperature T sub naught, which is 290 Kelvin, multiplied by the gain, which gives us the total noise, plus the noise associated with the first amplifier. And then the noise at the output, N sub naught, is the noise of the first stage, at the output of the first stage, multiplied by the gain of the second, times the noise introduced by the second stage. Okay, and then we have this result here. And so from here, we see that the equivalent noise temperature of the cascaded system is the equivalent noise of the first stage times the equivalent noise temperature of the second stage divided by the gain of the first. Okay, which when transformed to noise figure, okay, we have the following expression. And so you see that the noise associated with the second stage becomes divided by the gain of the first, and so has a much less contribution on the final system than the first. And so the main conclusion is that it is the first stage that defines the signal-to-noise ratio at the input. And so it's very important that the first stage is the one that introduces the least amount of noise. And so usually the first stage is a low noise amplifier. And so it's designed specifically to be a low noise amplifier. Okay, that's an important result. And now we are going to study this nonlinear distortion. Okay, as I said at the beginning, all electronic devices, they exhibit some kind of nonlinearity, which means if you apply a certain voltage at the input, the voltage depends not only on it's not only a linear gain or attenuation at the output of the signal, but has other terms. And so in general, to model a nonlinear device, we can use a Taylor series expansion of the output voltage. Okay. If the distortion is a simple one, usually called without memory, which means that it does not depend on frequency. So if it is a static nonlinearity, we can model this nonlinearity by using a Taylor series expansion of the input voltage, as we see here. And so the output voltage depends not only on this linear term, okay, on the input voltage, but depends also on the square and on the Q of and the higher order terms. And so we see that this term here is the linear term, right? And so if all the other terms will be zero, then the output voltage will be linearly proportional to the input voltage. And so this coefficient here, A sub 1, is the linear output coefficient. If A sub 1 is less than 1, then we have attenuation of the signal. If it is higher than 1, then we have a gain or an amplifier. The coefficient A sub 2 depends on the square, or is the coefficient of the square of the input signal, which means that in this case there's some kind of frequency conversion. If we have a signal Vi, which is the sine of omega 0 t, for example, right? Then Vi squared is the sine squared of omega 0 t. Okay. Let's assume that we have a sinusoidal input signal. V0 is the amplitude of the input signal, and omega 0 is the frequency of the input signal. And so if we expand this Taylor series, which is shown here, so we have a constant term here, we have the linear term here, and we have the square and the Q term, and so on. If we expand this cosine square as shown here, and the cube of the cosine, which is shown here, we see that here we have twice the frequency. Here we have, and then if we group together the terms at the same frequency, okay? So here we have the term at twice the frequency. But then there's another term. If we look carefully here, this cosine, the cube of the cosine, gives us a term which is the original frequency of the signal times 3 times the frequency, the third harmonic. The amplitude at the frequency of the input signal has 2 terms. One is the linear term, obviously, and the other term is the term that comes from this result here, okay, which depends on the coefficient A sub 3 and the cube of the amplitude of the signal, okay? And so the voltage gain at the frequency is given by this coefficient, which depends not only on the linear term, but also on the third term. Okay, and so the total voltage gain is A sub 1, linear term, times a factor that depends on the third order term. Okay, and this is an important point, because if we plot now, if we have an ideal amplifier, and if we plot the power over the input power, as shown here. So here we have output power, and here on the x-axis we have input power. If we, to obtain the power, and usually this plot is shown in a log scale, in dB, and so to convert this to dB, we have to multiply each side, calculate at each side times log of 10 of the input signal, and do the same at the output, at the right side of the equation. And so we get the left side gives us the output power, and here we have the an equation which, when represented on this plot, is a curve, is a straight line with a slope of 1. Okay, so this will be the y, this will be the x, and this is a constant term. Okay, or if you this will be y, equation like this, y equals a times x times b is a straight line. In this case, e is equal to 1, so this term equals 1, and so it means the slope of the curve is equal to 1. And so in this plot, a linear amplifier will be a straight line. But the problem is, due to the question is, this term here means that the gain, the actual gain of the amplifier will deviate from the linear, from the straight line. And usually A3 is negative, which means that as we increase the signal, the amplitude of the signal, this term starts to be more significant, because usually A3 is much smaller than A1, okay, in magnitude. And so for small values of the amplitude, the second term is usually small, but as we increase the amplitude, the second term starts to become significant and starts to deviate from the straight line. And so what happens is the following. Instead of following the straight line, the amplifier, which initially for small signals is close to the linear amplifier, ideal amplifier, then starts to deviate and starts to saturate as we increase the amplitude. Okay? And this saturation effect is a result of nonlinearity of the amplifier. Okay? And this is called gain compression, because as we increase the gain, as we increase the voltage, the gain starts to decrease. Okay? And so to characterize this gain compression, we define the 1 dB compression point, which is defined as the power level for which the output power decreases by 1 dB with respect to the linear amplifier. Okay? And so, which is shown here. So this will be the linear amplifier, and this is the deviation from the linear response. And when this difference here, when this difference from the linear case is 1 dB, then this is defined as the 1 dB compression point. So it corresponds to a point here, and this point can be referred to the input or can be referred to the output. So either way, okay? But let's see an example. Let's assume we have a device which has the following characteristics, which is shown here. So here we have amplitude gain of 15. This is the linear term. And then we have a third order term. So in this case, there's no second order, and all other order higher terms are 0. And here we have A3 is equal to -2. Okay? That's shown here. And so, in this case, the linear gain is just obtained by taking 10 log of 10 of the first order coefficient, which gives us 23.5 dB. Okay. If we want to calculate the input voltage at 1 dB compression point, by definition, the 1 dB compression point is where the gain is reduced by 1 dB. And so the gain of the amplifier is 10 log of 10 of this equation here. And the right side is the linear gain, which only depends on a 1, minus 1 dB. And so if we solve this equation for the amplitude V sub naught, we get the voltage referred to the input at which the gain reduces to 1 dB, which means that at 1.044 volts at the input, the gain will be reduced by 1 dB with respect to the linear case. Okay. Obviously, if we increase the voltage, then the gain reduces even further after that. Okay. And so, if we know the input voltage, then we can calculate the input power. For example, assuming output impedances of 50 ohm. And so we have the voltage, the mean average voltage, assuming we have a sine wave, the mean power is 1/2 of the V square over resistance. And this is given in dBm, that's why it comes multiplied by, because we have the power in dBm, okay, is the 10 log of 10 of the power divided by 1 milliwatt, or 10 to the minus 3. Divided by 10 to the minus 3, the equivalent of multiplying by 10 to the third, which is this factor here. So this factor 10 over 3 is just to make the conversion to dBm, or to refer to a 1 milliwatt. And so we get the result that the 1 dB compression point referred to the input is 10.4 approximately dBm. And the output power is obviously the input power P sub I minus 1 times the gain, the linear gain. Okay? And so it's 32.9 or 33 dBm output power. So far, we assumed that at the input we had just one sine wave, so a signal with just one frequency. Okay? Obviously, in practice, the signal is not composed of just one frequency, it's composed of different frequencies, right? And so the next case that we can study is when we have just two frequencies, okay, at the input, which is, and the mathematical calculations are shown here. And so the difference from previously is that in this case, the input signal is the combination of two sine waves at two different frequencies, omega 1 and omega 2. Yeah. Again, assuming nonlinear expansion, a Taylor series expansion of the input signal at the output. And so we have the linear term here, okay, and I have the square term, which is this one here, which has already been expanded. So it's the cosine square of this equation here, of the summation of two these cosines, which has been expanded here in this equation. And then we have the third term is this one here. And we are only assuming three terms up to third order, okay? And what we see is that the second order term, which is this one, has twice omega 1, has twice omega 2, and then there are two important terms here, which are the sum of the two frequencies, omega 1 plus omega 2, and then the difference frequencies, omega 1 minus omega 2. And so when we have two frequencies, we have the harmonics of the original frequencies, but then we have terms that corresponds to the combination of the frequencies of the input signal. And so we have the summation and the difference of frequencies. And so this is called the fact that we have two frequencies, and besides having the harmonics, we also have the combination of the sum and the difference, right? These terms are called beating terms, okay? In Português is batimento. São componentes resultantes do batimento entre as duas frequências. Because it depends on the terms cosine of omega 1 t times cosine of omega 2 t. And the product of two cosines corresponds to the beating, which gives the sum and the different frequencies. Okay? And then the third order term, which is this one here, has got the original frequencies, omega 1 and omega 2. But then we have third order harmonic of the original frequencies. And then we have also some very important terms, which are these ones here. Twice one frequency minus the other. Okay? And so the output spectrum consists of harmonics called intermodulation products of the form, which is shown here. An integer m times omega 1 plus another integer times omega 2, where n can be a positive or negative number. Okay. It is interesting to see this result in a diagram along the frequency. That's here. Okay. So we have the original frequencies, omega 1 and omega 2, which are these two signals here. Okay, you see them here. I can try to zoom in just for you to see better. So we have omega 1 and omega 2. Yeah. And then we have these terms here on the right side correspond to the terms of second order terms, twice the original frequencies and the summation of the two. We have another term here, omega 1, omega 2 minus omega 1, which is a second order term as well. And then we also have, which is very important, these third order terms, which are shown here. Okay? These are third order terms. You see that 3 times the original frequencies omega 1 plus omega 2 and 2 omega 2 plus omega 1, which are these two signals here. But then we have those that I mentioned before, these ones here. Okay. And so, which, as you see, they are very close to the original frequencies. Okay. For example, in cable TV applications, we have not just one carrier that transports the TV signal, but we have several channels, right? So in your cable TV system, you probably have 80, 100 channels, whatever. So we have a lot of them. And they are all usually multiplex over frequency, and they, in general, they are more or less equally spaced between each other. And so we would have, in a cable TV system, for example, we would have another channel here, and we have another one here, and another one there, and another one here, and so on. So we have a lot of channels spaced in frequencies, where each channel transports a certain TV signal over a certain bandwidth. Yeah, so we have all these signals multiplexed together over frequency. And what happens is that, for example, these two signals, the intermodulation distortion generated by the amplifier of these two signals, just that two, falls within the top of the adjacent TV channel. And it's not possible to remove this distortion, right? Because it's in a type of intermodulation distortion that falls within the adjacent channel that is not possible to remove. And so it's like noise that falls on top of the signal. And so it deteriorates the performance of the system and reduces the signal-to-noise ratio. Okay. And so these terms are very important ones, these ones here, which are close to the original frequencies. They usually fall, since they're very close, they fall in the transmission band, especially if we have a large amount of signals being multiplexed over frequency, as I said. And so they are not easily filtered and will cause distortion of the output. And this is called intermodulation distortion. Also, if you have, for example, an OFDM signal is a signal which is being transmitted in multiple carriers as well. So it's a signal that has several carriers very close together. Yes, so like this. And so if we pass this signal an amplifier which introduces some distortion, what happens is that it's an effect that it's called spectral regrowth. Because at the output of the amplifier, the signal we have additional frequencies. Some of those intermodulation distortion falls within the band, but some of it falls outside the band, and the terms that fall outside the band increase the noise or distortion and produces this spectral regrowth, because the spectra has additional frequencies which original were not there. Okay. And this is very important in wireless applications, especially in a transmitter. The last stage of amplification to provide sufficient power for sending the signal, to broadcast the signal, right, has to be a power amplifier to provide sufficient gain. And this power amplifier usually is operated near the distortion region, which may provide this kind of effects which are undesirable and affect the performance of the system. And so to measure the effect of the intermodulation distortion of an amplifier, we define the third order intersect point, okay? which is represented by this term here, P3, which is defined by the intersection of the linear response of an ideal amplifier with the power associated with these third-order intermodulation products. Okay, so we've seen that in a plot of output power, this plot of output power over the input power, the linear ideal case, linear case, is this curve which has a slope of 1. Okay, which is represented. And then what we have is that the power associated with this third-order intermodulation, which is this the magnitude of these third-order terms, this one here, has a certain power associated with it. Okay, is as we increase the input power, it increases as well, and then it increases more rapidly, and we've seen that depends on the cube of the amplitude of the signal, and so it increases like this, has a slope of 3, okay, because it depends on this voltage, input voltage square to the cube. And so it intersects the linear curve in a point which is precisely defined as the third-order intersect point. And this third-order intersect point is maybe used as a measure of the distortion introduced by the amplifier. If the amplifier introduces low distortion, if it has it's a low distortion amplifier, the third order intersect point will be higher or lower. What do you think?
Could you please repeat the question?
The third order intersect point defines the distortion of amplifier. And so it can be somewhere, if we refer the third order intersect point refer to the input, in this case we have a certain value here, but then we could have another amplifier that would have, for example, the slope is the same, but for example, we have another amplifier like this, and then the third order point will be here, right? So this one will be P3 dash, and this one is just P3. Which one? And so in this case, we have that P3 dash is higher than P3. Which one corresponds to a more linear amplifier?
Well, that one is linear until a higher power. So.
Exactly. So the one in blue, P3 dash, has a higher third order intersect point, corresponds to an amplifier with lower distortion, right? Because you can increase the power to a higher value until you reach the region of distortion. Okay, so the distortion will be lower. And so that's why this third order intersect point can be used to define the nonlinearity of the amplifier. It's a measure of the nonlinearity of the amplifier. If we try to obtain the value of P3 as a function of the coefficient, assuming that we have VI equals A naught plus A1 VI plus A2 VI squared and so on. Okay, assuming this nonlinear expansion, we can obtain P3 as a function of the parameters. And we see that it depends obviously on A3, the third order coefficient, has to, because it's related to the third order term. But we see that P3 is independent of the input power. Okay, and so it's a useful measure of the system nonlinearity, as I said. So far, we have obtained the following relations, where P sub naught is the ideal linear response, and then we have the response at frequency omega 1, which includes saturation, and then we have the response at the intermodulation and distortion, and based on these equations, let us now derive some relations between these expressions. So let us write P sub naught as 1/2 of A1 squared, the amplitude of the signal squared, and let's assume we have a resistance of 1 ohm to simplify the expressions, and at frequency omega 1 minus omega 2, this will be 1/2 of 9/16 A3 squared times V0 to the 6. Okay. At point P3, which we define as the third order intersect point, we have that at P3 the output voltage is the voltage at the intersect point P3, which we will call V sub IP, and in that case the linear response of the amplifier at P3 has an amplitude, by definition, which is equal to the amplitude of the internalization distortion. And so we can write 1/2 A1 square V IP squared from this equation here equals 1/2 of 9/16 A3 squared times V IP to the 16 to this power of 6. And so from this result we obtain that A1 squared equals 9/16 A3 squared times VIP to the power of 4, and which gives us that VIP equals 4/3 of A1 over A3, and P3 by definition is equal to P0 when the amplitude is equal to the amplitude at the intersect point, which gives us 1/2 A1 squared V square IP, which is equal to 2/3 of A1 to the power of 3 over A3, which is equation we have for the third order intersect point. We see that the third order intermodulation power varies with the power of 6 of the amplitude, where the linear response varies with the square of the amplitude. So if we take P naught to the power of 3 over P omega 1 minus omega 2, this gives us (1 over 8 A1 to the 6 V amplitude to the 6 9 over 32 times A3 square V 6. And the reason why we took the power of 3 of the linear response is because these both terms cancel out, and then we end up with an expression which is 32 over 8 times A1 to the 6 divided by 9 A3 squared, which equals 4 over 9 A1 6 over A3 squared, which is 2/3 of A1 to the cube over A3 squared, and this is equal to P3 squared. And so the final result that we were looking for is that the third order intermodulation power equals P to the cube to P3 squared, since this term here under parentheses is P3, or in dBm we have that P omega 1 minus omega 2 in dBm equals 3 P0 in dBm minus 2 P3 dBm, which is the expression we were looking for. Okay. So this equation tells us that if we know the linear response of the amplifier, and if we know the third order intersect point, we can obtain the amount of power at the third order intermodulation product. Okay. For example, assuming again the previous example that we had before, which was where the Taylor series expansion was given by this result, assuming a resistance of 50 ohm, we calculate the third order intersect point from this equation here in dBm. And if we assume that the input power is, so in this case, what we are doing in this diagram, if we, so we are assuming that we are operating at a specific point. Let's assume here. Let's assume we are operating somewhere here. So this value will be P omega 1, the input frequency. And we have a certain value of P output power at this point, and we have a certain third order intermodulation power. And so we have here a region that the third order intermodulation power is a certain dB below the linear power, which is calculated here. Okay, so we calculate the third order intermodulation power. So we calculate this point here, this one. We know that the input power is minus 10 dBm. We know what's the value of P3. So we obtain the third order intermodulation power, which is minus 117. And so by comparing with input power, we see that the intermodulation power is 107 dB below the fundamental component. Okay. The third order intermodulation product is changed if we cascade components. And the idea here in this slide is to obtain the result of the equivalent third order intermodulation point of a cascade of two components. So here we assume we have an amplifier with a certain third order intermodulation point, P3 dash, and I have another one which is P3 two dashes. And we want to obtain the equivalent third order intersect point of the cascade of these two components. Obviously, the gain of these two components is the product of the gains of each one individually. Okay, and the total distortion of the second stage, and so we have to remember that this first amplifier generates some distortion, omega 1 minus omega 2. So this one generates some distortion. The distortion generated by this amplifier is multiplied by the gain of the second at the output. So here at this point, this becomes multiplied by the gain, which is this factor here. Okay. But then the second amplifier also generates some distortion. And so we have to add an additional term, which is the result of the distortion introduced by the second amplifier, which is shown here. And so we have two terms. The first one is associated with the distortion of the first amplifier, P3 dash, and multiplied by the gain of the second. And then we have a second term, which is the distortion introduced by the second amplifier. And so if we calculate the equivalent third order intersect point from this equation here, we obtain this result here, which if you look carefully, obviously it depends on the third order intersect point of the second amplifier and the third order intersect point of the first amplifier multiplied by the second. One important example for it is when we have an amplifier followed by a mixer. Okay, so the amplifier amplifies the signal, and then the mixer combines this RF signal with a local oscillator to provide a frequency conversion of the signal. This is a common configuration to provide frequency conversion. Okay, and so the third order term of the amplifier amplifiers are usually referred to the output. And so this P3 dash, which is 22 dBm, is referred to the output, or 128 milliwatts. The mixer doesn't have gain, has a loss of 6 dB, and has a third order intersect point of 13 dBm, but referred to the input. Since one of the device has third order intersect point defined at the input and the other one at the output, to be able to do some calculations, we have to refer both to the same input or the output. And one way of doing this is by looking into this equation here. Okay. So, okay, if the second amplifier here has no distortion, okay, if it has no distortion, what's P3? The third order intersect point of a linear amplifier.
Should be infinite.
Infinite, because no matter what the input signal, the third order intersect point will be very large. Okay, so no distortion is infinite, which means that P3 dash double dash is equal to infinity. If we replace here, this term will be 1 over infinite will be 0, right? And in this case, P3 is simply equal to J2 times P3 dash, which is a reasonable result, right? Which says that if the second amplifier has no distortion, then the distortion of third order intersect point will be defined by the first amplifier only, and the total distortion is the distortion of the first amplifier multiplied by the gain of the second amplifier. Okay, which means that if we have a certain P3 referred to the input of the second amplifier, if we want to define the third order intersect point at the output of the amplifier, we just need to multiply by the gain. And so if we have a device where the third order intersect point is referred to the input, if we want to refer it to the output, we just need to multiply by the gain, or the other way around. If we have the P3 referred to the output and we want to refer it to the input, we need to divide it by the gain. Okay? So that's the way we have to do it. And so here, since we have one referred to the input and the other one referred to the output, we're going to refer P3, this one here, we're going to refer it to the output. So we have both at the output. And so multiplied by the gain. So multiplying by the gain is equivalent in a log scale of adding the value in dB. And so we have 13 dBm referred to the input, minus 6 dB because the gain is minus 6 because it's a loss. And so we have at the output P3, which is 7 dBm. Okay. And now by using the previous formula that we found for equivalent of a cascade of two components, so we have amplifier followed by the mixer, then if we apply this equation here, and remember that in this equation the values of G, the gain, and the third order intersect point that are all in a linear scale. Okay, and so we need to use P3 dash 158 milliwatts, which is shown here, multiplied by the gain of the second. A loss of 6 dB is equivalent to a gain of 0.25, which is shown here. And then P3 dash is 7 dBm or 5 milliwatts, which is this term here, which gives us 4.4 milliwatt or 6.4 dBm for the cascade of two components. We had initially the amplifier with a very large intersect point, but the mixer had an output third order intersect point of only 7 dBm, and so the result is mainly determined by the distortion of the mixer. Okay, because the component which has introduces higher distortion will be the dominant device, or will be the device that dominates the distortion, total distortion at the output, and so it will be mainly determined by the mixer in this case. Another important definition is dynamic range, and there are two possible definitions for dynamic range. The linear dynamic range, which is the range of powers which are limited at the low end by the noise and at the high end by the compression point, 1 dB compression point. Okay, and so in this curve here, so we have a 1 dB compression point, this point here. The noise of the system is represented here by this level. Okay, and so the linear dynamic range is the range where when the signal is very large, it's limited by the 1 dB compression point, which means we should not go over this power, otherwise we are introducing too much distortion on the output of the signal. And so at high level is limited by 1 dB compression point. But if we reduce the signal level, right, then the distortion will not be significant. But then if the signal is reduced to a very low level, then if the signal starts to be identical to noise, we can start not be able to recover the signal from the noise. And so at low end, the range is limited by the noise itself. This range is by definition the linear dynamic range. Okay? There's another definition which is the spurious-free dynamic range, which is the range over which the power level of distortion is below the noise. Okay? For example, if we are operating the device, for example, at this point, at a certain power here, then we have a certain signal level and a certain noise level, which is defined by this range here, right? The spurious-free dynamic range is the range where the point where the noise is identical to the distortion. It's the limit. So if we start with a very low noise power here, we see that the intermodulation power will be very low, much lower than the noise, right? If we start to increase the input power, the noise, the distortion level starts to increase. Okay? The noise is always the same. And when the distortion power becomes equal to the noise level, Slightly above this, then we start to see the distortion, power of the distortion starts to become noticeable. Okay, and so this is the point here where the noise is equal to the noise power, the distortion power, which defines precisely the spurious free dynamic range. The linear dynamic range is defined by 1 dB compression point divided by the noise level. And so in dB is the power of 1 dB compression point, dBm, minus the noise level. And the spurious free dynamic range is defined by the signal power divided by the distortion power at the point where the third order distortion power equals to the noise. Okay. And it's possible to show it that it's given by this equation here. So it's P3 over noise level to the power of 2/3. The spurious free dynamic range is defined as the ratio of the output power at the fundamental frequency over the power at the intermodulation distortion, when the intermodulation distortion level, the power level, is equal to the noise level. That's the definition. However, we know from previously that the intermodulation distortion level is equal to the output power of the linear amplifier divided by P3 squared. And when this condition is satisfied, this equals and sub naught noise level, from which we obtain that P03 equals and not P3 squared, from which we obtain that P naught, the power, output power of the linear level, equals n naught 1/3 times P3 2/3. And from this we get that the spurious free dynamic range, assuming that the power at the fundamental frequency is approximately equal to the linear power level, is P naught over N naught, and using the result we obtained previously and substituting in this equation, we get and noise level to the power of 1/3 times P3 2/3 divided by the noise level, from which you obtain that the dynamic range equals P3 over N naught to the power of 2/3, which was the result we were looking for. So let's see an example just to finish. Let's assume we have a receiver with a noise figure of 7 dB. 1 dB compression point referred to the output is 25 dBm. The gain of the amplifier is 40 dB and has a P3 of 35 dBm, also referred to the output. and the bandwidth is 100 megahertz. And this amplifier is connected to an antenna. This antenna is operating at a temperature 150 Kelvin, saying that the antenna is operating at this temperature is equivalent of saying that specifying the noise generated by the antenna itself, right? Because this antenna is generating some thermal noise, and the thermal noise is quantified in terms of this equivalent noise temperature. Okay. If we start to calculate the total output noise power, we know the noise figure of the amplifier, which is 7 dB. We need to convert the noise figure to equivalent noise temperature, which is this term here. F minus 1 times T sub naught is the equivalent noise temperature of the amplifier, okay, times the equivalent noise temperature of the antenna, gives us multiplied by K times B times the gain of the amplifier, gives us the total noise at the output, which is minus 47 dBm. Okay. And so from this result, we can determine the linear dynamic range, because it's P1 minus N naught in dB. So P1 is 25. The noise power, we have already calculated it from the previous result, which gives us 25 dBm minus 47, so it's plus 47, which gives 72 dB. Okay, so we can also calculate the spurious free dynamic range from the equation we had before, from this equation here, where we can calculate, knowing the third order intersect point and the noise level, we can calculate the spurious free dynamic range. And so will be 2/3 of P3 minus noise level is 54.9. And we see that the linear dynamic range is always larger. The one shown here in red is always larger than the spurious free dynamic range. So this range here is always larger than the spurious free dynamic range. So in this example, the linear dynamic range is 72 dB, and the spurious free dynamic range is 55 dB approximately. Just one comment here, the spurious free dynamic range sometimes refer to the minimum signal level that can be detected. If we have a signal to noise ratio required at the output of 10 dB, then the spurious free dynamic range referred to the minimum signal level is subtract the signal to noise ratio from this result. Okay.